Right. So breakthroughs in AI, how can we enable that using chiplets? And more importantly, how can we do that whilst maintaining chiplet interoperability? Well, that's what we have been doing with AMBA CHI chip-to-chip and what we want to talk to you about today. I'm myself, Francisco. I'm a product manager at ARM. I'm also here with Jonathon from Nvidia. And yeah, let's get down to it. So chiplets, well, it's becoming very, very clear, something we have been talking quite a lot here today. A lot of new opportunities that chiplets bring, but together with those opportunities, there are also a lot of new challenges, a lot of new requirements, particularly from a protocol point of view as well. Something just a few sessions ago, we were discussing the need for open standards, particularly in the protocol space, to ensure interoperability. Something we can all agree. We need open standards, and more than that, we need standards that are widely used, widely applicable, exactly for maximum interoperability. We also need flexibility in those protocols to interface with this wide variety of accelerators that are emerging, that perhaps have their own quirks, their own ways of managing memory, their own models, consistency models, and so on. Finally, we also need performance. We need protocols that can sustain very high bandwidth to feed the accelerators. Yep. And well, that's exactly what we are doing with the AMBA CHI chip-to-chip. As we were just discussing before, I think was it John who mentioned the work that we have been doing with AMBA. Here, what we are doing with AMBA CHI chip-to-chip, we are extending the existing AMBA CHI protocol to make it exactly suitable for connecting chiplets to chiplets. It's something that is complementary to a lot of the initiatives we are seeing, like UCIe, but also complementary to initiatives like the one we have at ARM with the chiplet system architecture, or CSA. Some of the benefits, but I'm not going to go too much in details now. We're going to go back to that later on. And before we dive into the specifics of the AMBA CHI chip-to-chip, I want to take a bit of time to talk a little bit about the motivation on specifically why are we starting from AMBA? Why are we not picking, let's say, or starting from a new blank sheet of paper, right? And I think the answer here is very simple. It's simply down to the fact that AMBA is the standard today for SoC communications. It's really at the very heart of the silicon IP marketplace. It is really at the heart of the fabless design, right? As we were discussing, AMBA is an open standard, widely used for almost 3 decades already. It's freely available. Anyone can go download and use it. It's platform neutral, more than proven in billions of devices, right? You may be familiar with some of the specifications like CHI, AXI, but it's really that ecosystem that brings AMBA to life. And then if we continue a little bit on the motivation and think of why did we pick CHI in particular, well, it's simply because it gives us that solid foundation. CHI is already a very high performance protocol. It's credited, and more importantly, it is already a fully coherent protocol, and we're going to dive into a little bit of why that is interesting here. And it's also a very low risk path, right? It's also widely used, proven as well. Thanks. So if we look into the architecture or the details of the CHI C2C itself, as I said, it's an extension to the existing on-chip CHI. And that's what I'm illustrating here in terms of this layered architecture, right? So on the very top, we have the existing AMBA CHI protocol, widely used. And with CHI chip-to-chip, the middle layer is really when we packetize that to make it suitable to be transported over fixed size containers, such as, for example, UCIe that I'm illustrating here, meaning the data link and the PHY. But equally, it could be used across a PCIe PHY or custom bespoke as well. And then finally, some of the benefits. Yeah, going back to the very beginning, what does it really mean in practice is, well, number one, you can reuse that same protocol. It means that you have consistency across your design. You don't need to do any protocol conversions. You reduce complexity, you reduce latency, and you can carry the same architecture features throughout your design. Reducing complexity and, of course, reducing latency. Talking about latency, we have done a lot of optimizations as well for latency and efficiency as well. And finally, as I said, because we follow this layered architecture, we reuse initiatives like UCIe. And where do we see this being used in terms of use cases or topologies? I'm illustrating some of them here. So obviously coherent SMP, that's where CHI has been traditionally used. But more importantly here in the case of AI for accelerator or device attach, right? For both the fully coherent, but also the IO or non-coherent. And it's really this superset of use cases that gives us the opportunity to have one single and unified interface protocol exactly for maximum interoperability. And then finally, talking about adoption, really want to take the opportunity here to thank the partners that have been collaborating with us to develop and to release the CHI chip-to-chip specification. I'm illustrating some of them here, but I really want to call out the collaboration we have been doing with Nvidia that has been really fundamental to the development of the CHI chip-to-chip. And well, the reason why we're here together with Jonathon. So with that, hand over to you.
Okay, thank you, Francisco. Yeah, so Nvidia, we've been working with ARM for several years to really help develop this CHI chip-to-chip protocol. And so today I wanted to give you a little bit of discussion about well, what does it take to interface an accelerator and why you might want to choose AMBA chip-to-chip as your protocol. So accelerators really kind of have three kind of major problems when you're trying to integrate them into a system. They often define their own ordering and consistency model, which may be different from your system architecture. They must support a very robust programming interface with the CPU, things like atomics, whatever programming interface they have. And then they also really have to scale. You need to scale up with bandwidth and various other needs that maybe you won't see in some other design. So I'm going to go touch on each of these points, go in a little more detail. So let's talk a little bit about accelerator ordering. If you decide to integrate an accelerator, you might end up with a heterogeneous system like this where, in this picture on the left-hand side, you have your traditional, in this case, maybe it's ARM host CPU architecture. You got your cores, your caches, last level cache, memory system, et cetera. And everything on that side follows the architecture reference for the host. So for example, this is in ARM, it's the ARM architecture reference manual that defines what your memory synchronization barriers look like, how loads of stores work, what atomics, all of the behavior of the CPU is well architected and defined in the CPU world. But on the other side, you have a very different beast. You have an accelerator. So I'm going to use the example of an Nvidia GPU because that's the one I know the best and most dear to me. But it's completely different than how a CPU works. It's very weakly ordered. And ARM's already weakly ordered, but the GPU is even more so. It's got a very different hierarchy where synchronization is defined within these different scope levels where you have threads that synchronize within an SM, within something called a CTA. Those have a wider scope of the entire GPU, and there's an even a wider scope of synchronization, which is the entire system, which is back to the CPU. And how all this works and is defined is in the Compute Unified Device Architecture model, or CUDA, and so you can go look up all the details, but it's really unique to the GPU, and it's also one of the ways the GPUs really get a lot of their performance and acceleration. And that's really defined by the accelerator and the needs of whatever workload you're accelerating. So this is a GPU case, but you might have some other accelerator or something else that you're building that works very differently. So I also want to talk a little bit about the accelerator programming interface. And I wanted to point out it's complicated. You're not really meant to read this slide. This is just an example of one operation that you can see in the CUDA C++ interface. And these are all the different types of atomic adds you can do. And when you think about it, why would you have 11 different varieties of an atomic operation? And that's really just shows to the complexity of what you're doing when you're doing an accelerator. These are all different data types. There are different formats. There's small floating point. There's integer, different sizes of integers. Vector. These are all the sort of things you want to do. And today you could try to support these on something like PCIe, but PCIe only has a couple different atomic flavors today. And all of these are something that you'd have to add into your protocol. Every time you want to go do another flavor, you've got to go put that into your protocol, do something different. And one way where chai chip to chip really gives you a lot of power to hide this complexity is that you can have coherency. So when you have a coherent interface, a lot of this complexity is just handled on the accelerator side. If I want to go do one of these complex operations, I can take the memory over to the accelerator, do whatever operation I want to do, and then the CPU can go ahead and access it back. And so what I've taken is like 11 different forms of atomic add, and now I just have to go use this protocol to check the memory out and handle it in a way that makes it fit into the CPU programming model. I don't have to do any special on the CPU side. Your system just kind of works, right? And so that's one of the advantages of something like chai chip to chip, which is a coherent model. It really lets you simplify the model as you see in the wider system. So another challenge is really looking at how accelerators scale. And Francisco mentioned this, but the memory model of devices, often accelerators, are designed so that they can scale across many interfaces. You don't have a lot of built-in ordering. You don't necessarily want, PCIe has a very strict ordering model. Writes and reads have a very specific model. But those sort of orderings don't necessarily lend themselves to fast acceleration that you might need if you're building your own AI accelerator. And so one thing that's nice about chai chip to chip is that the way the protocol is defined is that most of the requests are independent. And there are some, you go look at the spec, and I think there's a link later on where you can go download and look at it. Most of the chai requests are independent. You don't end up with any artificial ordering. That's really up to you to structure your system so that you can avoid it. There are a few rules where things are ordered, but that's really for making performance well when you start talking about these cross-chip links, because there are some things that you might want to do that a little differently when you're cross versus on. But this really lets you do things like stripe your requests across a huge number of links, and then you can get aggregate bandwidth, which you might not get if you just stuck building one link with one interface. And you don't really see that with your traditional, as I mentioned, AXI and PCIe systems. So really, when you think about it, like what goes into a protocol, right? And why would you want to pick something like ARM chip to chip? So, I talked about some of the other things like really defining your accelerator architecture, but the value here is that this is a native interface for the ARM ecosystem and a lot of the chip ecosystems. There's no remapping here. You don't have to change your semantics. There's not like a different ordering rule or something different you have to do. Both sides, if you want to be able to speak this, just has the right mechanisms. One thing people don't think about a lot is like there can often be deadlocks or interactions, especially when you start talking about coherency protocol. And if you look at something like chai chip to chip, it has all of the native channels and all the different independent things you need to make sure that you don't create a deadlock. You don't have to map back and forth between one architecture or another. Almost on time. Another great value, as we talked about, is it has supports the full rich set of architectural features. So things like confidential compute architecture, which is popular and is important for servers, coherency, I mentioned atomics, even memory taking extension. Any of those things you might do that fit within the ARM and the CHI ecosystem or AMBA ecosystem, you can now support that natively with this protocol without having to, once again, to change everything. Another big advantage is that it's symmetric. There are some protocols where the host and the device have a different input, and by being symmetric, it really lets you support the same set of operations from the accelerator and the SoC. And that goes into the next comment, which is that it's flexible because it's symmetric, because it's flexible, you can use the same interface if you're building a single die and you're sticking your accelerator in the die, or you're going to disaggregate and build a chiplet for accelerator and a host SoC. You can actually use the same interface, right? Because you don't have to go suddenly be, I'm doing PCIe now. I just have the same native interface no matter where I've stuck the die. And it also lets you potentially think of other designs where maybe if you put some SoC functionality into your accelerator chiplet, I think somebody was talking about beachfronts in an earlier discussion. You may need to put some of your memory interfaces in your accelerator, and you want to treat that like host design. You really have an option to do that because you can put some of that functionality across the two different dies. So really what's advantage about this protocol is it really is kind of a native protocol for how you're doing system and SoC integration, and that lets you pick where you want to put something within the system. So the last slide we have is how to get involved. I don't know, Francisco, you want to help people how they can.
Thanks. Just wrapping things up, how to get involved. Here's some pointers. First of all, to download the spec from our website, freely available. some more information about how we got there, the collaboration with the industry, and then if you want to have more information about AMBA as a whole, otherwise feel free to reach out. We're both going to be here after the talk as well. Thank you so much.
Thank you, Francisco and Jonathan.